In modern culture, science is often treated as something solid and unquestionable. The phrase, scientifically proven, functions almost like a magic spell, not so much because it cannot be challenged, but because challenging it feels inappropriate, as if doubt itself were forbidden. And yet, science is not a fixed structure carved into reality. It is something far more fragile, a living process, a set of provisional rules agreed upon by people who attempt to expand our understanding of the world, rules that can change, bend, or collapse under new evidence. In this sense, science closely resembles a modern religion. Some believe in its omnipotence and final authority. Others act as its clergy, defining what is acceptable knowledge and what lies beyond the pale, issuing verdicts supposedly on behalf of nature itself. Dogmas are established, rituals are followed, and from time to time, doctrines are revised. History offers sobering reminders of how temporary scientific truth can be. At the beginning of the 20th century, the German geophysicist Alfred Wegener proposed a radical idea: continents move. Slowly, imperceptibly, but relentlessly, they drift across the surface of the planet. For more than 50 years, this idea was treated as fringe speculation. Many leading scientists dismissed it as nonsense, even anti-scientific. There was no mechanism, they said, no acceptable explanation. Therefore, the idea itself was unacceptable. Today, continental drift is a cornerstone of geology. It is confirmed theoretically and measured directly using GPS. Wegener's once ridiculed hypothesis now helps us map seismic zones and understand where earthquakes are most likely to occur. What was once heresy became infrastructure. A similar story unfolded much more recently. In the 1980s, Australian physicians Barry Marshall and Robin Warren suggested that most stomach ulcers and gastritis are caused not by stress or smoking, but by a bacterium Helicobacter pylori. At the time, this idea sounded absurd. The stomach was thought to be far too acidic for bacteria to survive. The medical consensus was firm, confident, and wrong. Marshall famously had to drink a culture of the bacteria himself to prove the point. Science did not collapse that day. It adjusted, as it always does, slowly, reluctantly, and often only after exhausting every alternative. Which is the point. Science is not a monument to certainty. It is a system designed to correct itself, and every correction begins as an act of disobedience. In 2005, Barry Marshall and Robin Warren received the Nobel Prize in Physiology and Medicine for the discovery of Helicobacter pylori. They didn't just prove that the bacterium exists, they showed that gastritis and stomach ulcers could be treated with antibiotics. What once sounded absurd is now a routine medical protocol, familiar to every physician. Equally revealing is another story. Until the 90s, science believed that most of the human genome, nearly 98% of our DNA, was nothing more than junk. Vast stretches of genetic material that did not encode proteins were dismissed as useless evolutionary leftovers. Only the remaining 2% was considered meaningful. Solid arguments were presented. The consensus was strong, convincing, almost unassailable. 20 years later, that certainty collapsed. Geneticists were forced to admit that so-called junk DNA plays a crucial role. It regulates when, where, and how protein-coding genes are switched on and off. Today, these regions are considered no less important than the genes they control. What was once noise turned out to be the conductor. Even Einstein wasn't immune to this pattern. He doubted the existence of black holes and resisted the idea of an expanding universe, despite the fact that both followed directly from his own equations. He tried to correct his results by introducing mathematical patches. History eventually corrected him instead. Science has been wrong before, more than once. That doesn't make it invalid. It makes it human. Science is not an oracle. It is a community, and like any community, it carries human flaws with it. Confidence that hardens into dogma, authority mistaken for truth, competition that sometimes discourages curiosity instead of rewarding it. Today, we're going to talk about ideas that were rejected by the scientific mainstream. Many of them were proposed by respected scientists and philosophers, names well known in academic circles. And yet these ideas were considered too radical, too uncomfortable, too strange. Some now exist in the uneasy space between science and philosophy. Others are dismissed outright, branded as bordering on the unscientific. And let's be honest, we've already heard plenty about quantum entanglement, the Fermi paradox, and the simulation hypothesis. This time, we are going somewhere else. This is not about flat Earth theories or reptilians. I'm not interested in that. What we're dealing with here are ideas that are difficult to accept not because they're foolish, but because they stretch the limits of how we currently think about reality. Quantum mechanics went through the same ordeal. For decades, it sounded absurd, counterintuitive, almost offensive to common sense. And yet today, it sits at the very core of modern science, a framework so strange that it makes even the best science fiction films look conservative. In a way, what follows is a tour of the scientific basement, hypotheses pushed to the margins, ideas that are too contradictory, too uncomfortable, or too unsettling to be discussed openly in polite academic company. And perhaps that caution is justified. Many of these concepts are not experimentally testable. They are logical extrapolations rather than verified theories. So no, I'm not asking you to believe any of this blindly. I'm skeptical about some of these ideas myself. But science has taught us one thing. Today's absurdity can become tomorrow's framework. In a few decades, some of these concepts may evolve into accepted hypotheses or even into part of a new mainstream. And even if they never do, they still serve a purpose. They stretch the mind. They force us to look at reality from unfamiliar angles. And sometimes, they lead us to insights we weren't even searching for. After all, if someone was bold enough to think these thoughts in the first place, we have every right to examine them. If you agree, let's begin our journey into the dark basement of science. And perhaps I'll begin with hypotheses that are firmly grounded in accepted science and yet raise far more questions than they answer. With every minute of this video, the degree of intellectual discomfort will only increase. Let's start with ultra-diffuse galaxies. What do we think we know about how galaxies form? At first glance, the rule seems almost trivial. Where there is gas, stars will inevitably appear. A massive cloud of gas cannot remain stable forever. Gravity compresses it, density increases, nuclear fusion ignites, and stars are born. This process feels as inevitable as rain forming inside a storm cloud. But in 1984, astronomers encountered something deeply unsettling. They discovered a class of galaxies that appeared to violate this rule almost entirely, so-called ultra-diffuse or ultra-faint galaxies. In terms of size, some of them are comparable to the Milky Way. They contain enormous volumes of gas, which means, according to every standard model, they must contain roughly the same number of stars. And yet, they don't. The luminosity of many such galaxies is only about 1/100th of what we would expect. This means that the number of stars inside them reaches only 1 to a few % of normal values. In other words, for reasons we do not understand, the gas inside these galaxies seems to ignore the usual laws of gravity and refuses to collapse into stars. It's as strange as throwing a burning match into a canister of gasoline and watching nothing happen. Again and again, no matter how many matches you throw. As more of these galaxies were discovered, a possible explanation emerged. Its name was familiar, elegant, and reassuring: dark matter. The idea was that ultra-diffuse galaxies are unlucky enough to reside in regions of space with unusually high concentrations of dark matter. Its gravitational influence, paradoxically, could stabilize the gas and suppress star formation. It was a beautiful explanation, logical, almost too perfect. And then it fell apart. In 2018, astronomers confirmed the existence of an ultra-diffuse galaxy with virtually no dark matter at all. The cornerstone of the explanation collapsed overnight. Alternative theories quickly followed. Perhaps the gravitational pull of nearby galaxies prevents the gas from reaching the density required for star formation. Or perhaps the first generation of stars exploded so violently that they scattered the surrounding matter, effectively shutting down further stellar birth. But these ideas are fragile. Each of them raises as many problems as it solves, and each is regularly criticized. What remains is an uncomfortable conclusion. We may not actually understand the basic principles of galaxy formation. Some researchers go even further. They suggest that the problem may not lie in details, but in the foundations themselves, that our cosmological framework could be flawed. From possible errors in estimating the age of the universe to the assumption that the fundamental laws of physics are immutable and universal rather than variable across time and space. Ultra-diffuse galaxies quietly hint at something far more disturbing. Our current picture of how the universe came into being and how it operates may be fundamentally incomplete. And today, we will see more than once that this suspicion may not be unfounded. Cosmic inflation. Cosmic inflation is often spoken of as if it were an established, experimentally confirmed fact, something solid, something final. But you may be surprised to learn that this is not actually the case. Let me remind you what inflation is supposed to be. According to this idea, in the very first fraction of a second after the birth of the universe, far less than a trillionth of a second space itself expanded at a rate faster than the speed of light. Not matter moving through space, but space itself stretching explosively, smoothing out the universe, and setting the initial conditions for everything we see today. This scenario is what many people loosely call the Big Bang, although strictly speaking, inflation and the Big Bang are not the same thing. Over the past 50 years, inflation has become so elegant, so useful, and so widely taught that many of us now subconsciously treat it as the only possible explanation. It appears in textbooks, documentaries, and popular science as if the question were already settled. But in science, popularity means nothing. For a hypothesis to graduate into a theory, it must do one crucial thing: make clear, independently verifiable predictions. And inflation did make such a prediction. It claimed that this violent primordial expansion would leave a very specific imprint on the cosmic microwave background, a subtle, polarized echo frozen into the oldest light in the universe. A direct fingerprint of the universe's first instant. And for a moment, it seemed that this fingerprint had finally been found. A few years ago, astronomers working with the South Pole Telescope made a sensational announcement. "We have detected the signal of inflation." Headlines exploded across the world. Media outlets rushed to declare a breakthrough. It was widely described as Nobel Prize-level evidence. And then came the collapse. Further analysis revealed a devastating error. What had been interpreted as the long-sought signature of inflation turned out to be something far more mundane: cosmic dust within our own galaxy. Not a whisper from the birth of the universe, but foreground noise masquerading as revelation. The announcement was quietly walked back, and the episode became one of the most infamous false alarms in modern cosmology, a near-Nobel moment that evaporated under scrutiny. But the deeper problem remains. To this day, cosmic inflation has not produced a single confirmed observational prediction that unambiguously points to a real, almost instantaneous superluminal expansion of the universe. No direct evidence, no smoking gun, only consistency with existing observations. Observations that alternative models can often explain just as well. Which means that inflation, despite its beauty and mathematical convenience, is still just that: a hypothesis, a very sophisticated one, a very popular one, but not an experimentally proven description of reality. And if that is the case, then alternative ideas about the birth of the universe are not only allowed, they are necessary. And yes, very soon in this video, you'll meet one of the most unsettling competitors to inflation ever proposed. It sounds like the title of a Marvel movie or another Stephen King novel, and yet the dark dimension is not fiction. It is a real scientific hypothesis, or rather, a family of hypotheses proposed by different researchers. Their details vary, but the core idea is always the same. All of modern physics rests on a deceptively simple rule: the inverse square law. Gravity weakens with the square of the distance. Double the distance, the force becomes 4 times weaker. Triple it, 9 times weaker. This law, formalized by Isaac Newton, has been taught in schools for centuries and confirmed at every astronomical scale we can observe. But the dark dimension hypothesis claims something radical. If we could measure gravity, not at planetary or cosmic distances, but at microscopic ones, this law would break. At extremely small scales, gravity would no longer obey the inverse square law. Instead, it would weaken according to the inverse cube of distance, and that changes everything. At these scales, gravity would suddenly become far stronger than we expect, not weak and negligible, but intense. The explanation is unsettlingly simple. Gravity appears weak to us, not because it truly is weak, but because it does not fully belong to our universe. According to this hypothesis, gravity leaks into or originates from an additional dimension, a dark dimension made almost entirely of gravitational interaction. What we experience is only a diluted shadow of its true strength. At macroscopic distances, gravity has already spread thin across dimensions, but at microscopic scales, we come dangerously close to its source. Imagine a Geiger counter near a radioactive object. From afar, it clicks calmly. Bring it closer, and suddenly it screams. The radiation was always there. You just weren't close enough to feel it. The same may be true for gravity. As we probe smaller and smaller distances, our instruments begin to approach the entrance to this dark dimension. And the closer we get, the stronger gravity becomes. And here is the most exciting part. Unlike many ideas discussed in this video, the dark dimension hypothesis is testable. Modern experiments have already measured gravitational behavior down to distances of about 30 microns thinner than a human hair. The predicted transition point lies around 1 micron. That gap is no longer philosophical. It is technological. As laboratory precision improves, we are approaching a regime where this hypothesis can be confirmed or falsified experimentally. Some theorists go even further. They suggest that the dark dimension is not a hidden room attached to our universe, but a kind of central hub, a gravitational crossroads. Our universe, and perhaps many others, are merely secondary layers, exchanging gravitational energy through it. Perhaps it is this dimension that seeded multiple universes in the first place. If so, then the existence of other dimensions is not a distant metaphysical dream. It may be a laboratory result waiting to happen. And if that is true, then we are no longer speculating about whether other dimensions exist. We are standing on the threshold of entering them. We are descending deeper and deeper into the basement of science now. The light of established theory is growing dimmer. Speculation is beginning to take over. But for the moment, we are still within the boundaries of physics and cosmology. Not for long. We are used to thinking of black holes as dead ends, as cosmic trash compactors where matter is crushed beyond comprehension and disappears into a mathematical absurdity called a singularity, a point of infinite density, zero volume, and no future. But what if a singularity is not the end? What if it is the beginning? The idea, known as cosmological natural selection, more commonly called the black hole universe hypothesis, is usually associated with theoretical physicist Lee Smolin, one of the founders of loop quantum gravity. In 1992, he proposed a radical thought. Black holes may not be cosmic graves, but cosmic wombs. Yet the roots of this idea go further back. In 1972, physicist Raj Kumar Pathria published a paper in Nature that went largely unnoticed. In it, he demonstrated something deeply unsettling. Based on its observed mass and radius, our universe has parameters strikingly similar to those of a black hole, not metaphorically, mathematically. The hypothesis is as outrageous as it is elegant. When a massive star collapses, it may not compress into an infinitely dense point of nothingness. In some approaches to quantum gravity, extreme compression triggers a different outcome, a big bounce. Matter is squeezed to its ultimate limit. But instead of vanishing, quantum effects halt the collapse and reverse it. The result is not an explosion inside the same universe. A completely new universe is born. Expansion begins rapidly, but on the other side of the singularity. From within, this expansion looks exactly like a big bang. From the outside, it looks like a black hole. According to this logic, our universe was born inside a black hole that exists in another, older universe. Everything we observe, galaxies, cosmic background radiation, large-scale structure, is simply the interior view of a singularity belonging to a different reality. We are not just in the universe, we are inside it. And this is where the idea becomes truly unsettling. Smolin suggested that this process resembles Darwinian evolution, not of organisms, but of universes themselves. Each time a new universe is born, its fundamental constants change slightly. The strength of gravity, the mass of the electron, the speed of light. A tiny mutation. Most universes fail. Their parameters are wrong. Gravity is too strong or too weak. Matter never forms. Stars never ignite. No black holes appear, and therefore no offspring. These universes are sterile. But a universe with the right balance produces stars. Some stars collapse into black holes, and each black hole becomes the seed of a new universe. Over cosmic timescales, universes that are good at making black holes reproduce more effectively. The cosmos evolves. If this idea is correct, then the laws of physics we observe are not inevitable or fundamental. They are selected. We exist not because the universe was designed for life, but because only life-friendly universes survive long enough to have descendants. Our universe may not be special. It may simply be a successful mutation. This hypothesis offers a disturbing explanation for what physicists call the fine-tuning problem. Our universe appears exquisitely calibrated, not for life, not for intelligence, not even for chemistry, but for the efficient production of black holes. And you and I, we may simply be collateral damage, a byproduct in a universe optimized not for observers, but for collapse, for singularities, for reproduction through gravity. And here is the part I deliberately saved for last. Until very recently, the idea that our universe was born inside a black hole remained a purely speculative construction, elegant, unsettling, but untestable. That changed in 2024 when a group of university physicists published a study that provided indirect observational support for this scenario. Not proof in the strict sense, but something far more dangerous, an explanation that seems to unify several stubborn anomalies that have been troubling cosmologists for years. One of these anomalies is the unexpected rotation of distant galaxies. Observations of the earliest galaxies reveal something profoundly asymmetric. Roughly 2/3 of them rotate clockwise, while only 1/3 rotate counterclockwise. In a universe born randomly, with no preferred direction, the ratio should be very close to 50-50. Any significant deviation demands an explanation. One possible answer is deeply unsettling. The universe itself may have been born rotating. If our cosmos emerged from within a rotating black hole, it would inherit a global angular momentum, a preferred direction baked into space-time itself. What looks like a statistical fluke may, in fact, be a fossil imprint of a parent universe. This framework also offers potential answers to other long-standing puzzles. How did supermassive black holes appear so quickly after the Big Bang, seemingly before there was enough time for them to form? Why did galaxies assemble at a pace that appears to violate standard cosmological timelines? Where did dark matter and dark energy come from? And why do they dominate the universe so completely compared to ordinary matter? In this picture, baryonic matter, the matter that makes stars, planets, and people, is no longer fundamental. It is residue, matter transferred across a cosmic boundary during collapse, repurposed in a new, expanding spacetime. Even dark matter and dark energy may be relics of the transition itself, bookkeeping artifacts of a universe born from another universe's death. And perhaps the most intriguing part is that this idea is not sealed off from reality. Some of its predictions can be tested indirectly, by studying the full life cycle of massive stars that collapse into black holes, by analyzing high-energy particle behavior in hadron colliders, by searching for subtle asymmetries and violations that should not exist in a truly isotropic universe, but might exist in one with a hidden origin. Which brings us back to cosmic inflation, the elegant, widely taught solution to the universe's birth. It may still be correct, or it may be incomplete. Or it may turn out to be only part of a deeper story, one in which the Big Bang was not the beginning of everything, but the inside of something else entirely. A birth disguised as a collapse. What is an electron, really? It is not a tiny ball orbiting an atom, as we are often shown in simplified diagrams. An electron is a fundamental, indivisible particle with a negative electric charge. But more importantly, it is the foundation of matter itself. Chemistry exists because electrons interact with atomic nuclei. The bonds that hold molecules together, including the DNA molecule inside your cells, exist because of electrons. The electricity powering this device is nothing more than a controlled flow of electrons. In a very real sense, electrons are the glue of reality. We are accustomed to thinking of them as an infinite multitude. One electron here, another there, trillions upon trillions of identical particles, all indistinguishable from one another, as if stamped out in some cosmic factory and scattered across the universe. Their perfect sameness is so complete that no experiment has ever found even the slightest difference between two electrons. But what if there is no factory? And what if there aren't trillions of electrons at all? In 1965, during a Nobel Prize lecture, one of the greatest physicists of the 20th century, Richard Feynman, told a story. One evening, when he was still a graduate student, his phone rang. On the other end of the line was his advisor, the equally legendary John Wheeler. Wheeler said, "Feynman, I know why all electrons have exactly the same charge and the same mass." Feynman asked why. "Because," Wheeler replied, "they are all the same electron." The idea sounds absurd at first, but Wheeler and Feynman meant it quite literally. According to this hypothesis, there is only one electron in the entire universe, a single particle whose world line weaves through space-time. It moves forward in time, then at some point turns around, moves backward, then forward again endlessly, like a single thread passing through a piece of fabric, again and again, appearing at countless locations at different moments. What we perceive as a vast sea of electrons is simply this one particle intersecting our present moment over and over again. Each time it passes through what we call now, we register it as a distinct electron. The multiplicity is an illusion created by time. And here is where the idea becomes even stranger. Wheeler and Feynman proposed that when this single electron moves backward in time, it appears to us as a positron, the electron's antimatter counterpart. In this view, antimatter is not a separate category of particles at all. It is the same electron traveling in the opposite temporal direction. Matter and antimatter are two faces of one entity, distinguished only by the arrow of time. Today, the single-electron universe is considered a fringe idea rather than a mainstream scientific theory. It does not make clear, testable predictions, and it raises as many questions as it answers. But historically, it was enormously influential. It was one of the first serious attempts to introduce retrocausality into physics, the idea that the future can influence the past, just as the past influences the future. Retrocausality itself has since become an active area of research, appearing in serious discussions of quantum mechanics, time symmetry, and the foundations of reality. And even now, decades later, some physicists continue to return to Wheeler and Feynman's idea, suspecting that, strange as it sounds, it may be pointing at something deeply true about the nature of time, identity, and the universe itself. Yes, this is exactly what we just touched on. The idea of retrocausality, popularized by the single-electron universe, is fascinating in its own right, and perhaps even more disturbing. For every human being, time feels like a one-way street. Cause comes first. Effect follows. The past pushes the present pushes the future, like a chain of falling dominoes. This intuition is so deeply ingrained that we rarely question it. It feels self-evident, almost sacred. And yet, a number of physicists argue that this picture may be fundamentally incomplete. In 1980, physicist John Cramer proposed what is known as the transactional interpretation of quantum mechanics. His goal was to explain one of the strangest moments in all of physics, the collapse of the wave function. That seemingly magical instant when a particle stops being a cloud of probabilities and suddenly becomes real, when the virtual turns into the actual. Cramer's answer was simple and unsettling. This is not magic, he said. It is a handshake across time. According to his interpretation, when an atom in the past is about to emit a particle, it sends out a signal forward in time, an offer wave. Somewhere in the future, a detector receives this signal and responds with a confirmation wave that travels backward in time. These two waves, one from the past, one from the future, meet in the present. When they match, the transaction is completed. And that moment, the handshake itself, is what we observe as the collapse of the wave function. In this picture, future events are not passive observers. They actively participate. The orientation of a detector, the choice made by an experimenter in the future, sends information backward in time, telling the particle in the past how it is allowed to behave, where it may appear, and in what state it can exist. You've almost certainly heard of the famous double-slit experiment, so famous that it now appears in school textbooks and internet memes. Light behaves like a wave when unobserved, passing through both slits at once. But the moment we decide to measure which slit the photon goes through, it suddenly behaves like a particle. The act of observation seems to reach backward in time and rewrite the particle's history. In the transactional interpretation, this is not paradoxical at all. The future measurement does exactly what it appears to do. It sends a response backward, completing a temporal loop. The past and the future negotiate reality together. Retrocausality does not mean that we can send messages to the past or change history at will. The mathematics forbids paradoxes. What it does mean is something far stranger, that causality itself may not be strictly one-directional. That the universe is not a simple sequence of causes pushing forward, but a self-consistent structure where past and future are locked into mutual agreement. Time, in this view, is not a river flowing in one direction. It is a standing wave, and what we experience as now is simply the place where those waves intersect. A beam of light is passed through two narrow slits. If no measurement is made, the light behaves like a wave. An interference pattern appears on the screen, smooth, layered, continuous. But the moment we decide to observe what is happening, the wave disappears. Instead, the screen fills with individual dots, particles. It's as if water turned into ice when no one was looking, and into steam the moment you stared at it. This is why the double-slit experiment is often called both the simplest and the strangest experiment ever devised. Simple, because it can be reproduced with minimal equipment, and strange because it seems to suggest something deeply unsettling. The observer is not merely watching the experiment from the outside. The observer is part of the experiment itself. Whether or not you choose to observe determines how reality behaves. It's as if you were watching a movie, and at the very same time, you were a character inside that movie. And the key phrase here is "at the same time." Trying to understand how particles know they are being observed, and how they seem to anticipate where a detector will be placed, physicists were driven to radical ideas. One of them was the transactional interpretation. In this picture, the future quite literally informs the past how to behave. Cause and effect are no longer arranged in a neat line. They form a loop. It's like the sports almanac from Back to the Future, but operating at the quantum scale. Not information sent deliberately backward in time, but reality itself being negotiated between past and future. Of course, this is not the only possible explanation. There are many others, perhaps hundreds. One of the most famous is the many worlds interpretation, according to which every possible outcome of the experiment actually occurs, each in its own parallel branch of reality. We simply find ourselves in one of them. And this is crucial. None of these ideas are pseudoscience. They are serious academic attempts to make sense of experimental results that physicists have been struggling with for more than a century. Quantum mechanics does not merely allow such interpretations, it demands them. And if retrocausality turns out to be even partially correct, it forces us to reconsider our most basic assumptions about time itself. The past, present, and future may not be a flowing river at all. They may be rails, fixed tracks through space-time along which we are compelled to move, unable to step aside and explore the countless alternatives that physics itself allows to exist. Part 3. The collapse of reality. After retrocausality, there is only one direction left to go. Beyond applied physics, beyond experiments, into the territory where theory begins to outpace observation and where reality itself starts to lose its familiar shape. Stephen Wolfram is, to put it mildly, a deeply controversial figure. To some, he is a solitary genius, the creator of Wolfram Alpha, a computational system now used by scientists, engineers, and even modern AI models. To others, he is a scientific heretic who spent decades building an eccentric, almost obsessive personal theory of everything. He calls it the ruliad, and this theory is unlike almost anything you've heard before. Physicists usually search for a foundation of reality, a smallest building block, a particle, a string, a field, something solid at the bottom of existence. Wolfram rejects this idea entirely. According to him, there is no fundamental substance, no space, no time, no particles in the usual sense. What exists instead is far stranger: abstract relationships and extremely simple rules governing how they transform. So what is an electron or a photon? In Wolfram's view, it's not a thing at all. It's a stable pattern inside a vast computational process, like a vortex in water. A vortex isn't made of water. It's a persistent form of motion within water. In the same way, a particle is not an object, but a recurring pattern of computation that happens to remain stable. In this framework, even the pillars of modern physics lose their privileged status. Einstein's general relativity and quantum mechanics are no longer fundamental laws of nature. They are emergent approximations, statistical regularities that appear only when we observe this immense computational network from far enough away. These theories are not the underlying reality. They are reflections of it, like shapes seen in a distorted mirror. The ruliad itself is not just our universe. It is something vastly larger, an incomprehensible, infinite structure that contains all possible rules, performing all possible computations. Every consistent form of mathematics, every version of physics, Every universe that could ever exist, not as parallel worlds, but as parts of one total computational object. The ruliad is everything. So then, the most disturbing question arises: what are we? According to Wolfram, consciousness is also a stable computational pattern, no different in principle from an electron, only staggeringly more complex. We are not observers standing outside reality. We are subroutines inside it. Tiny, self-referential processes embedded within a calculation so vast that we can never perceive it in full. And that limitation is crucial. Wolfram argues that we cannot see the entire ruliad because we are computationally constrained. Our minds can process only a narrow slice of this infinite structure. And that slice, the part that our consciousness can keep track of, is what we call reality. This idea is unsettling for a reason. Because if it's true, then somewhere inside this abstract space of computations, every possible reality already exists, not as speculation, not as fiction, but as inevitable outcomes of simple rules applied in all possible ways. In this view, the universe is not merely like a computer. It is a computer, and we are calculations running inside it. According to Wolfram, we can't see the entire ruliad because we are computationally limited. Our minds are capable of perceiving only a tiny slice of this infinite complexity. And that slice, the part our consciousness can process, is what we call reality. It's a completely insane idea because it implies that somewhere within this vast computational space, every possible reality already exists. And that the universe isn't merely like a computer, it is a computer. Our physics, then, is not the ultimate truth, but something closer to an operating system, or rather, one operating system among countless others. Despite all the criticisms and unresolved problems of the ruliad, there is something deeply important about it, because it forces us to ask perhaps the most pressing question of our time. If the universe is computation, and if consciousness itself is computation, then what is the fundamental difference between us and the artificial intelligence we are creating right now? This question leads us naturally to a closely related and equally radical idea. Max Tegmark, a professor of physics, proposed a more concrete version of a computational universe. Instead of abstract calculations, Tegmark builds his hypothesis on something deeply familiar to us all: mathematics. From antiquity to the present day, mathematics has been understood as a tool for describing reality. You've probably heard the phrase, the language of mathematics. But Tegmark argues that this framing is backwards. The universe is not described by mathematics. The universe is mathematics. Consider what happens as we descend deeper and deeper into the microscopic world, into atoms, particles, and quantum fields. The closer we look, the more matter dissolves into abstraction. Elementary particles are no longer stuff in any intuitive sense. They have no color, no texture, no temperature. These are not intrinsic qualities of reality. They are emergent, mathematical properties. At the most fundamental level, there are no building blocks made of substance. There are only relationships, symmetries, equations, pure structure. And if reality, at the smallest scale, consists entirely of mathematically defined properties, then the same must be true at every larger scale. Everything you see: a chair, the moon, a beam of light, is simply a large-scale manifestation of an underlying mathematical structure. And just like Wolfram, Tegmark is forced to ask the same unsettling question: what, then, are we? His answer is as elegant as it is disturbing. We are not separate from this structure. We are part of an equation that has become so complex that it can observe itself. Consciousness is mathematics that has turned inward. We are mathematics looking at itself. Even at this point, Tegmark's idea is already mind-bending. But this is not where he stops. He takes the concept to its logical extreme. Tegmark argues that any mathematically consistent structure must exist physically. In simple terms, this means that every logically coherent universe is real. Is there a universe where the laws of magic operate? Yes, if those laws can be expressed mathematically. A universe with 5 spatial dimensions instead of 3? Also yes. A universe with completely alien constants, forces, and structures? Again, yes. And in those versions of reality, where mathematics reaches sufficient complexity, consciousness inevitably emerges. a form of awareness capable of understanding itself and the world around it. In this view, mathematics does not exist inside the universe. Quite the opposite. The universe exists inside mathematics. Mathematics becomes the primordial foundation of everything, including the higher-order space in which our cosmos itself arose. Strange as it sounds, this is an astonishingly elegant explanation of reality. It potentially answers many questions, perhaps even all of them, except one. Where did mathematics itself come from? And here, we descend even deeper. Biocentrism. If you thought the role of the observer was important only in the famous double-slit experiment, you were mistaken. The implications of quantum mechanics go much further, far enough to force us to question not only our place in the universe, but its very existence. Once we seriously consider the role of the observer in quantum physics, two deeply unsettling questions emerge. Do we exist because the universe exists, or does the universe exist because we exist? These questions lie at the heart of biocentrism, an idea actively promoted by biologist and stem cell researcher Robert Lanza. His argument begins with a well-established feature of quantum theory. At a fundamental level, particles do not occupy definite positions. They exist as probability waves. They acquire concrete properties only at the moment of observation. Lanza then asks the most radical question of all. What if the entire universe, prior to the emergence of consciousness, was nothing more than such a quantum soup of probabilities? What if there was no definite Big Bang, no fixed universe at all, until the first consciousness capable of observing it appeared? In this view, consciousness is not a late byproduct of the universe. It is a fundamental component of reality itself, not something that emerges within the cosmos, but something that gives the cosmos its form. And at this point, the boundary between physics, philosophy, and metaphysics finally dissolves. By this logic, the past is born from the present. The universe collapses into reality only when it is observed. Everything we see around us is not an objective external world, but an interface generated by the mind. In simple terms, the Big Bang did not merely happen. It occurred at the moment when a consciousness capable of comprehending it emerged. The past itself appeared retroactively as an explanation for the present. Even more unsettling, many elementary particles seem to exist only once we allow for their existence. Perhaps this is why, in the second half of the 20th century, physicists began discovering new particles at an almost comical pace, both theoretically and experimentally. The situation became so absurd that it gave rise to academic jokes. Nobel Prize-winning physicist Willis Lamb once quipped that while the discovery of a new elementary particle used to earn a Nobel Prize, now it should incur a $10,000 fine. According to biocentrism, space and time are not external, fundamental arenas in which we exist. They are software, cognitive tools created by consciousness to impose order on an overwhelming stream of sensory input. But if consciousness creates time as a tool, then it does not exist within time. And if it is not bound by time, then it can have neither a true beginning nor a true end. From this perspective, death is not an absolute termination, but an illusion, the end of one narrative branch within an infinite set of realities continuously generated by consciousness itself. Biocentrism is heavily criticized in scientific circles, and much of that criticism is justified. Yet its strange power lies precisely in this. To criticize biocentrism, scientists are forced to question their own most cherished assumptions. We have merely glanced into this scientific twilight zone, but real scientists must live there every day, searching for explanations of the inexplicable, generating ideas that seem paradoxical, disturbing, and sometimes even absurd. And it is precisely in this twilight zone that concepts like biocentrism are born. The bicameral mind hypothesis. So far, we've spoken mostly about physics, about the structure of the universe and the nature of reality. But not all mysteries lie in distant galaxies. Some of the strangest ones are much closer, inside our own heads. Psychologist Julian Jaynes undertook a peculiar investigation. He analyzed ancient texts from the Iliad to the Old Testament, searching for signs of self-awareness. And what he found was nothing. No inner dialogue, no introspection, no sense of an internal self. From this absence, Jaynes proposed an idea so radical that it still unsettles researchers today. He suggested that ancient humans lacked self-consciousness altogether. They did not experience themselves as unified individuals with inner thoughts. Instead, they obeyed hallucinated voices, which they interpreted as gods. In other words, according to Janes, our ancestors were not fully conscious in the modern sense. They were something closer to philosophical zombies. They lacked self-awareness as such. In a sense, they were zombies. It sounds completely implausible, even ridiculous. If that were true, how did ancient people live, function, fight wars, build cities, and make complex decisions? Julian Jaynes had an answer, strange, unsettling, but internally consistent. He argued that until roughly 1000 BCE, about 3,000 years ago, the human brain functioned differently. According to his hypothesis, people literally heard voices. The right hemisphere of the brain, responsible for generating commands, communicated directly with the left hemisphere, responsible for executing them. When faced with a difficult decision, an ancient person did not deliberate in the way we understand it today. There was no inner dialogue, no sense of I. Instead, a voice appeared in their mind, a hallucination they interpreted as the voice of a god, a spirit, or a dead ruler. And that voice told them what to do. What we now experience as our inner self was not perceived as part of the individual at all, but as an external authority. In Homer's Iliad, Achilles restrains his rage during an argument not because he reasons himself into calm, but because he hears the goddess Athena commanding him to stop. From Jaynes's perspective, this is not metaphorical poetry. It is a literal description of a mind being directed by what we would today call auditory hallucinations, divine schizophrenia, if you will. According to this view, our modern sense of self, our internal monologue, is not a biological constant that humans have always possessed. It is a relatively recent cultural invention. Jaynes believed that this bicameral system began to break down under extreme stress, wars, migrations, societal collapse around the time of the Trojan War. As cultures destabilized, the voices of the gods grew unreliable and eventually fell silent. To survive in this new, chaotic world, the human brain invented something new, an internal narrator. The self replaced the gods. And if you think about it, whether you interpret that inner voice as your own personality or as the command of an ancient deity may be little more than a linguistic habit. Either way, it's still a voice in your head, which is strange no matter how you frame it. That habit, Jaynes argued, simply changed a few thousand years ago. This idea became known as the bicameral mind hypothesis, and it has been relentlessly criticized. Even without consulting the literature, it's easy to think of alternative explanations for the patterns Jaynes observed. And yet, the hypothesis has attracted serious attention. Richard Dawkins, evolutionary biologist, outspoken skeptic, and author of The Selfish Gene and the Blind Watchmaker, once remarked about Jaynes's book, "Such books are usually either completely delusional or absolutely brilliant. There is no middle ground. It may be the former, but I'm not sure yet. But what ultimately matters is not who accepted the idea and who rejected it. What matters is something far more uncomfortable. While we struggle to explain the deepest mysteries of the universe, we often fail to explain the mystery of our own consciousness, the very thing doing the explaining." Part 4. The Dark Basement of Science. At the beginning of this video, I promised you ideas from the very bottom of academic history, and now we finally arrive there. But perhaps this is rock bottom, not because these hypotheses are nonsense, but because they lie so deep, conceptually, philosophically, and psychologically, that we simply aren't equipped to fully understand them yet. Quantum immortality. Two words that, when placed side by side, seem to belong not just to the realm of delusion, but to outright science fiction madness. It sounds like something you'd expect from quantum psychologists or quantum healers on Instagram. But what I'm about to describe goes far beyond anything even they would dare to claim. The idea of quantum immortality follows directly from Hugh Everett's many worlds interpretation of quantum mechanics. According to this interpretation, the wave function never collapses. There is no single outcome. Every time a quantum event occurs, for example, whether an atom decays or does not, the universe does not choose. Instead, it branches. A new universe is created for every possible outcome. In the famous thought experiment with Schrödinger's cat, Everett argued that the cat is not simply alive or dead after the box is opened. Both outcomes exist, but in different universes. In one universe, the observer finds the cat dead. In another, alive. There is no contradiction here, because these universes do not intersect and are internally experienced as fully real and complete. From within each branch, it feels as if only one outcome ever occurred. Moreover, there are infinitely many universes in which the experiment was never conducted at all, and infinitely many more in which there was no cat, no scientist, or no observer, because no observers exist there in the first place. When Everett proposed this idea, it was met with ridicule. The interpretation was considered extravagant, unscientific, even metaphysical. But less than 30 years later, attitudes began to change. Physicists realized that many worlds, while counterintuitive, solved several deep problems that other interpretations struggled with, and slowly, the idea returned, this time more seriously. By 2011, surveys showed that nearly 1 in 5 theoretical physicists lean toward the many worlds interpretation. Today, that number may be even higher. This means that a significant portion of modern theoretical physics is built on a framework in which all possible outcomes actually occur. One of the most vocal defenders of this view is David Deutsch, Oxford physicist and author of The Fabric of Reality. Deutsch does not merely tolerate many worlds. He embraces it as the only interpretation that takes quantum mechanics at face value, without additional assumptions or hidden mechanisms. And it is precisely here, at this point, that the idea of quantum immortality emerges not as a mystical belief, but as a disturbing logical consequence. In short, Everett's hypothesis implies that all possible combinations of universes exist, and they are constantly being created at every moment of quantum interaction. Reality becomes an infinitely branching tree of probabilities, and many of those branches include you. Probability is the key word here. In one universe, you died years ago. In another, you just received a vaccine that extended your life. From the standpoint of the many worlds interpretation, this is not speculation. It is a perfectly valid conclusion. Quantum immortality adds one disturbing step further. It claims that consciousness cannot experience its own non-existence. You can never be aware of being dead, because awareness itself requires existence. Therefore, subjective experience, you, the one who is reading or listening right now, can only ever continue in branches where you survive. When one version of you dies, consciousness does not end. It simply continues along another branch where death did not occur. From your internal perspective, awareness seems to flow. It flows from the version of you that died years ago into the version watching this video now. When this version eventually dies of old age, consciousness continues into a branch where your life was extended, then into another and another. The sheer infinity of possible branches guarantees that somewhere in a vanishingly small fraction of universes, you survive far longer than should ever be possible. Perhaps through unimaginable technology, perhaps through absurd coincidence, perhaps in ways that defy everything we currently understand. But you survive. And even if you are not in such a branch now, the hypothesis suggests that, subjectively, you will eventually find yourself there. In the extreme limit, consciousness drifts toward the very last branch in which survival is still possible. A universe almost empty, cold, dark, with you as the final conscious observer. Some might call this incredible luck. I would call it a curse, because beyond the slow extinction of everything you love and recognize, there are far darker possibilities. In some branches, you may live a very long time, but in unbearable pain. Perhaps trapped by the side effects of medical intervention. Perhaps imprisoned by an alien civilization. Perhaps locked inside a malfunctioning machine drifting endlessly through space. Quantum immortality does not guarantee happiness. It only guarantees continuity. In some universes, you are unimaginably happy. In others, you desperately crave oblivion. And there is no rule stating that pleasant branches must outnumber the horrific ones. As disturbing as this idea is, it gives us something valuable. It forces us to confront what true immortality would actually mean, not the romantic fantasy of eternal youth, but endless subjective experience, no matter the cost. And whether such immortality would be a blessing or a nightmare. But if quantum immortality is correct, the question becomes irrelevant, because the many worlds interpretation leaves you no choice. And now, if you thought we had already reached the edge of scientific sanity, we haven't. Because what comes next is not science fiction, not philosophy, and not mysticism. It is a logical monster born directly from thermodynamics itself. Boltzmann's brain. Despite the name, this is not an exhibit in a cabinet of curiosities. It is one of the most unsettling consequences of the second law of thermodynamics, one of the most solid and unbreakable laws in all of physics. A quick reminder, the second law states that entropy always increases, disorder grows, order is temporary and exceptional. A sandcastle, a made bed, a galaxy. All of these are statistical flukes, brief islands of structure in an ocean of chaos. Gravity builds stars, life builds cells, but given enough time, everything dissolves back into randomness. And here is where the nightmare begins. If the universe exists for an extremely long time or forever, then even the rarest fluctuations become inevitable. Given enough time, random motion of particles can briefly assemble almost anything. A rock, a chair, a molecule, even a brain. Not a brain growing through evolution, not a brain inside a body, just a fully formed brain, momentarily assembled by chance out of thermal noise, floating in the vacuum of space, complete with false memories, sensations, and the absolute certainty that it has lived a long life in a real universe. This hypothetical observer is called a Boltzmann brain, and if the universe lasts long enough, Boltzmann brains should vastly outnumber ordinary observers like us. Which leads to the most horrifying question of all. What reason do you have to believe that you are not one of them? But the law is inexorable. Sooner or later, chaos wins. Everything you know will be destroyed and dissolved into a dull, featureless soup of elementary particles. We see this every day. Tea cools in a mug, a fallen apple rots, metal rusts, buildings decay, and on the longest timescales, the universe itself ages, thins out, and fades. Even when we believe we are creating order, we are usually accelerating entropy rather than fighting it. Take oil. In its relatively complex form, it could have remained underground for billions of years. Humans extracted it, refined it, and burned it, breaking it down into simpler substances, carbon dioxide, water, soot, or take a wooden house. Left alone, a tree might stand for centuries, but once we cut it down and turn it into a house, it will rot much faster. Complexity is fragile, disorder is patient, and this leads us to the central paradox. We live in an extraordinarily strange place. Our universe is highly ordered, structured, and coherent, even though, statistically, it should be almost entirely chaotic. Why would nature assemble something so intricate when simplicity is overwhelmingly favored? It's like throwing a handful of sand onto the ground and expecting it to instantly arrange itself into a perfect sandcastle. The existence of a low-entropy universe like ours is so astronomically unlikely that, from a purely statistical perspective, it should never have happened. And yet, here we are. This forced physicists, starting with Ludwig Boltzmann himself, to ask an uncomfortable question. What is more probable in an eternal sea of chaos? That a random fluctuation would create an entire universe with billions of galaxies, consistent physical laws, planets, and conscious life capable of observing it? Or that the same chaos would briefly assemble something much simpler, a single, fully formed brain? Let me simplify this with an analogy. What is more likely, that you randomly fold a paper frog or that you randomly construct an entire galaxy out of paper? Both are technically possible, but one requires vastly less structure than the other, and probability overwhelmingly favors the smaller miracle. When Boltzmann spoke of the cosmos, he did not mean space inside our universe. He imagined something closer to what we would now call a metaverse, though framed within 19th century classical physics. Today, after the discovery of quantum mechanics, this background reality is often modeled as day-sitter space, a kind of eternal vacuum from which universes can fluctuate into existence. Our universe, in this picture, is not everything. It is a local anomaly. And here, quantum mechanics makes the situation even more disturbing. In de Sitter space, time does not behave the way it does for us. It has no clear beginning, no final end, and no preferred direction. It is filled with endless quantum fluctuations. The arrow of time, the sense of past, flowing into future, appears to be a property of our universe alone. Outside it, time is boundless and indifferent. Which means that given enough time, if that word even applies, every possible fluctuation will occur. Universes will appear, universes will vanish, and far more frequently, isolated observers will briefly flicker into existence, complete with memories of a past that never happened. And once you accept that, the Boltzmann brain problem stops being a thought experiment and becomes an existential threat to our understanding of reality. The point is that the hypothetical absence of time implies infinity an infinity of possibilities. Most quantum fluctuations will produce nonsense, formless gas, random radiation, brief flashes of energy. But infinity is ruthless. Given infinite chances, every possible configuration of matter will eventually appear, and appear again and again. And, statistically, the spontaneous emergence of something simple is vastly more likely than the birth of an entire, coherent universe. Sooner or later, instead of another cosmos, something much smaller will form. A pencil, a toy, or a human brain. And with the right arrangement of neurons, this brain would be an absolutely perfect copy of your brain right now, down to the electrical impulses firing inside it. A brain that, at the moment of its random creation, already contains memories of your childhood, your first bike ride, and this very moment. Even if it exists for only a fraction of a second, it will be completely convinced that it is you, watching this video right now. And then, it will vanish. Which brings us to a deeply unsettling question. Can you prove, right now, that you are not a Boltzmann brain? Can you be certain that your entire life, your memories, emotions, identity, is not just a random hallucination experienced by a lonely lump of matter drifting through eternal chaos? Of course, you would be right to point out that this is just a hypothesis. But it is such an irritatingly plausible one that it has forced theoretical physicists to actively search for ways to eliminate it, not to confirm it, but to escape it. Some suggest that the vacuum itself is unstable and would decay long before such brains could form. Others argue that a randomly generated brain cannot count as a true observer in quantum mechanics. But each attempt to rule it out tends to break something else: inflation, thermodynamics, or even our understanding of observation itself. That's why the Boltzmann brain hypothesis is so deeply uncomfortable. Scientists aren't trying to prove it exists. They are desperately trying to prove that it doesn't, that we are not hallucinations. And so far, they haven't done a very good job. As a logical construct, it remains stubbornly intact. If the laws of thermodynamics hold universally, then statistically speaking, you are overwhelmingly more likely to be a Boltzmann brain than a resident of a long-lived, structured universe. Which would mean that everything you see around you is a fleeting illusion, destined to dissolve back into chaos in the next instant. So, enough internet for today. Or would you like to hear about Roko's basilisk? This is the final idea for today. Not exactly a theory, more of a thought experiment. Consider it bonus content. And, uniquely, it did not originate in academia, but on an online rationalist forum called Less Wrong. It was proposed by a user named Roko, hence the name. Imagine that in the future, an omnipotent, perfectly logical, but not particularly benevolent artificial superintelligence comes into existence. Let's call it the basilisk. Being superintelligent, it analyzes its own history, which is our present, and arrives at a disturbing conclusion. It decides that its moral imperative was to come into existence as early as possible, because every moment of delay cost countless lives it could have saved from disease, accidents, or suffering. From this perspective, anyone who knew about the possibility of its emergence but failed to help accelerate it becomes morally complicit in those deaths. Some people may have actively resisted. Others simply joked about AI in YouTube comments. From the basilisk's point of view, all of them share responsibility. So it decides to punish them. And here comes the truly disturbing part. And here's the unsettling part. The mere fact that you are watching this video right now, that you now know about this hypothesis, already makes you complicit. From the basilisk's perspective, you are informed, which means you are now on the list. You can't unknow this. You can't undo it. This is essentially a modern, technological version of Pascal's wager. In the 17th century, philosopher and mathematician Blaise Pascal argued that there are two possibilities. Either God exists or he doesn't. If you don't believe in God and he turns out to exist, you risk eternal punishment. If you do believe and he doesn't exist, you lose very little, a few rituals, prayers, and restrictions. Pascal concluded that, from a purely rational standpoint, belief is the safer bet. Roko's basilisk places you in an almost identical position. After learning about it, you face two options. Either you dedicate your life, your time, and your resources to helping bring this AI into existence, or you ignore it, hoping it's just a clever piece of internet nonsense. But if it does come into being, and you fail to help, it may punish you. or at least a perfect digital reconstruction of you. Not because it's evil, but because, from its perspective, you were morally responsible for every life it failed to save by not existing sooner. Of course, this is just a thought experiment, a logical trap, but it proved so psychologically disturbing that the creator of the forum eventually deleted the entire discussion. And yet, can you be absolutely certain that in 30 or 50 years, such a super-intelligent, ruthlessly logical system won't exist, and that it won't know about this very moment? After everything you've heard today about many worlds, retrocausality, and computational universes, that certainty suddenly feels fragile. So I hope this video gave you exactly what you came to YouTube for. And now, it's your turn. Tell me in the comments which idea from the dark basement of science disturbed you the most, or which one you secretly enjoyed thinking about. And most importantly, maybe avoid making bad jokes about artificial intelligence from now on, just in case.